What if I told you the universe has been whispering its secrets to us for billions of years, and we're only just beginning to listen? Picture this: the faintest hums, the quietest echoes, vibrations traveling across unfathomable distances, carrying the very story of how everything began. These aren't just random noises floating through space. They're cosmic messages encoded in the fabric of reality itself, waiting to be decoded. And what they reveal could rewrite our understanding of existence. Think about the last time you heard a sound that sent chills down your spine, maybe the rumble of distant thunder or the haunting melody of a song you couldn't forget. Now imagine that same feeling, but multiplied by the scale of the cosmos. The universe is alive with sound, from the deep, resonant pulses of colliding black holes to the delicate shimmer of starlight vibrating through the void. These interstellar sounds are more than just scientific curiosities. They're the fingerprints of creation, the echoes of events so ancient they predate stars, planets, even time as we know it. So how do we tune into this celestial symphony? Scientists have become cosmic detectives, using cutting-edge technology to capture and interpret these otherworldly vibrations. Every hum, every ripple in space-time is a clue, a piece of the puzzle that tells us how the universe expanded, how galaxies formed, and perhaps even what existed before the Big Bang. It's like listening to a recording of the universe's first breath, and the more we hear, the more we realize these sounds aren't just about the past. They're about us, the atoms in your body, the stars above you, the very air you breathe. All of it was born from those primordial vibrations. So let's lean in and listen closely, because the universe is telling us its story. And it's one you won't want to miss. You might be wondering, how can sound exist in space if there's no air to carry it? Here's the fascinating truth. While the vacuum of space means traditional sound waves can't travel the way they do on Earth, the universe is still bursting with vibrations we can translate into sound. Think of it like this: just because you can't hear a radio wave doesn't mean it isn't there. Scientists use specialized instruments to detect electromagnetic pulses, plasma oscillations, and gravitational ripples, then convert them into frequencies our ears can process. The result, a symphony of cosmic noise that tells us more than silence ever could. Take black holes, for instance. When two of these colossal objects collide, they send shockwaves through the very fabric of space-time, ripples so powerful we've detected them billions of light years away. By shifting these gravitational waves into the audible range, researchers have uncovered something astonishing. Black holes don't just merge silently. They ring like a bell, their pitch and decay revealing their size, spin, and even the shape of the universe around them. Then there's the sun, a constant roar of charged particles, solar flares, and magnetic storms. When translated, these eruptions sound like crackling fire or the deep, rhythmic thrum of a heartbeat. Each of these cosmic vibrations is a data point, a piece of evidence helping us reconstruct the hidden mechanics of the universe. But why go through the trouble of turning these signals into sound at all? Because our ears are remarkably good at detecting patterns. A scientist might stare at a graph of radio waves for hours and miss a subtle shift, but when that same data becomes a melody, an irregularity stands out like a wrong note in a song. It's how we've discovered pulsars, dense, spinning stars that emit precise musical beats, or mapped the magnetic fields of distant galaxies by listening to their faint interstellar hum. Sound, in this context, isn't just a curiosity. It's a tool, one that lets us hear the universe's secrets in ways our eyes alone could never perceive. And as our technology grows more sensitive, who knows what other melodies are waiting to be uncovered? Imagine rewinding time all the way back to when the universe was just a newborn, 380,000 years old to be exact. That's when the first sound escaped into the cosmos, not as vibrations in air, but as ripples in a searing hot plasma that filled all of space. Today, we hear its echo as the cosmic microwave background, a faint glow permeating every corner of the sky. This isn't just static, it's the universe's baby picture imprinted with the very first sound waves ever to exist. Those waves tell a dramatic story. In the universe's earliest moments, matter wasn't smoothly distributed. Tiny quantum fluctuations, random blips smaller than an atom, created regions where particles were packed slightly tighter or looser. As the universe expanded, these differences stretched into vast sound waves, cresting and collapsing through the primordial soup. When the cosmos finally cooled enough for atoms to form, releasing light from the plasma's grip, those waves froze in place, leaving behind a snapshot of their peaks and valleys. Today, we see them as subtle temperature variations in the CMB, warmer spots where matter was compressed, cooler spots where it was sparse. But here's what's truly mind-blowing. Those microscopic wrinkles became the blueprint for everything. Over billions of years, gravity amplified them, pulling matter into the denser regions until galaxies, stars, and planets emerged. The CMB is like a fingerprint. The same patterns that sculpted the Great Wall of Galaxies also shaped the room you're sitting in. Scientists decode these patterns with instruments like the Planck satellite, mapping the CMB's harmonics with such precision. They can even tell us how fast the universe is expanding or how much dark matter it contains. What does this ancient hum sound like when we translate it? Stretched across space and time, its original frequencies dropped to a deep, resonant bass, a tone far lower than human ears could detect. But when sped up, it becomes a haunting, otherworldly chord, vibrating at 50 octaves below middle C. It's the closest we'll ever get to hearing the birth cry of the cosmos. And just like a lullaby carries the essence of its composer, this sound holds clues to forces we're still unraveling: dark energy, inflation, even the possibility of other universes. The CMB isn't just a relic, it's a conversation, one that started 13.8 billion years ago and is still whispering to us today. Black holes aren't the silent voids we once imagined. They're cosmic orchestras, playing the deepest, most resonant notes in the universe. When two of these gravitational giants spiral toward each other, they don't collide quietly. Instead, they send shockwaves rippling through space-time, vibrations so profound we can hear them across billions of light years. Scientists call these signals chirps, brief, rising tones that start as a low hum and crescendo into a final, crashing note as the black holes merge. But these aren't just eerie sounds, they're precise cosmic fingerprints. The pitch of a chirp reveals the black hole's masses, while its duration tells us how far away they are. It's like listening to a cosmic tuning fork where every vibration holds a secret. Then there's the drone, the steady, ominous hum of a black hole's accretion disk. Picture a whirlpool of superheated gas and dust, spinning at nearly the speed of light as it's pulled toward the event horizon. The friction and magnetic fields in this chaotic disk create oscillations, which the Event Horizon Telescope translated into a sound 57 octaves below middle C. Shifted into our hearing range, it's a low, haunting rumble like the groan of a distant storm. But this isn't just atmospheric noise. The tone's fluctuations tell us how matter behaves under extreme gravity, how it warps, fractures, and ultimately vanishes. What's even more astonishing is how these sounds help us test Einstein's theories. When black holes merge, their gravitational waves ring out in specific harmonics, like a bell struck in a cathedral. If Einstein's predictions were wrong, those tones would sound off-key. But so far, every chirp matches his equations with uncanny precision. It's as if the universe itself is confirming relativity through song. And sometimes, these collisions leave behind a remnant black hole that continues to vibrate, emitting a fading hum like a struck gong. By studying these ring-down tones, scientists can measure the black hole's final shape and spin details that might one day reveal if there's more to gravity than we currently understand. But why stop at listening? These sounds are reshaping astronomy. Before gravitational wave detectors, black holes were nearly invisible. Now, we're building a sonic map of the cosmos, where collisions we'd never see with telescopes announce themselves in vibrations. Some black holes sing in frequencies too low for any instrument to catch their waves might take years to oscillate just once. Others, like the supermassive black hole at our galaxy's center, may be humming a constant, ultra-deep bass note we haven't yet detected. The universe isn't just showing us its secrets, it's singing them, and with every note we decode, we're learning to hear the music of the invisible. Neutron stars are nature's most precise metronomes, cosmic timekeepers so accurate, they rival our best atomic clocks. Born from the explosive deaths of massive stars, these ultra-dense remnants pack more mass than the Sun into a sphere no wider than a city. But what makes them truly extraordinary isn't just their density, it's their rhythm. As they spin, beams of radiation sweep across space like a lighthouse, hitting Earth in perfectly timed pulses. Convert those pulses into sound, and you'll hear something uncanny, a steady, rapid-fire ticking like a clock ticking at hyperspeed. Some neutron stars, called millisecond pulsars, rotate hundreds of times per second, their beats so rapid they blur into a high-pitched whir. Others, like the famous pulsar at the heart of the Crab Nebula, thump slower but with thunderous intensity, their pulses crackling with energy. Each of these cosmic drumbeats carries a wealth of information. The slightest hiccup in their rhythm, a subtle change in tempo or a skipped pulse, can reveal planets orbiting the star, or even the ghostly tug of gravitational waves warping space-time around it. But pulsars aren't just celestial curiosities. They're also some of the most rigorous tests of Einstein's theory of relativity. Picture a pair of neutron stars locked in a deadly dance, spiraling closer with each orbit. As they move, they radiate gravitational waves, losing energy and slowing their spins in predictable ways. By comparing the pulsars ticking to our own atomic clocks, scientists have confirmed Einstein's predictions with near-perfect precision. The timing is so exact, it's like measuring the distance between Earth and the Moon down to the width of a single hair. And then there are the glitches, sudden, mysterious speed-ups in a neutron star's spin. These aren't random malfunctions, they're windows into the star's bizarre interior, where protons and electrons are crushed into a quantum soup of neutrons and stranger particles. When the star's crust cracks under unimaginable pressure, or its superfluid core sloshes unpredictably, the entire star jolts like a skipping record. By listening to these glitches, researchers are piecing together the physics of matter at densities so extreme they defy earthly experiments. What's even wilder? Some pulsars act as cosmic anchors for interstellar navigation. Their predictable pulses are so reliable, NASA has proposed using them as a galactic GPS, a network of celestial beacons to guide spacecraft across the Milky Way. Imagine a future where explorers tune into the steady beat of a neutron star to find their way home. It's a reminder that the universe isn't just a silent void. It's a symphony of rhythms, each one keeping time in ways we're only beginning to understand. And with every pulse we capture, we're not just hearing the stars, we're decoding the very heartbeat of the cosmos. Long before telescopes or satellites, ancient philosophers dreamed of a celestial harmony, a hidden music woven into the movement of planets and stars. Pythagoras called it the music of the spheres, a symphony so perfect human ears couldn't perceive it. What's astonishing is how close they were to the truth. We now know the cosmos does vibrate with music, not metaphorically, but in literal, measurable frequencies. Take our own sun, for example. Its surface churns with constant oscillations, rising and falling in rhythmic waves like the skin of a colossal drum. These aren't random tremors, they're standing waves created by pressure bouncing between the sun's core and outer layers, ringing out at precise frequencies that reveal what's happening deep inside. Scientists call this field heliosysmology, the study of the sun's vibrations, and it works much like how geologists use earthquakes to map Earth's interior. By tracking millions of these solar oscillations, researchers can reconstruct the sun's hidden structure, from the churning plasma near its surface to the nuclear furnace at its heart. But the sun isn't the only star singing. NASA's Kepler mission turned its sensitive ears to distant suns and discovered something extraordinary: starquakes. These aren't quakes in the traditional sense. They're fluctuations in a star's brightness caused by sound waves trapped inside its interior, making the entire star resonate like a struck bell. The pitch of these stellar vibrations tells us everything. A young, massive star might hum in a bright, high-frequency tone, while an aging red giant thrums with a deep, slow bass. Some stars even exhibit mixed harmonics, their surfaces flickering with overlapping waves that hint at complex internal dynamics. It's as if every star has its own unique voice, a fingerprint of sound that reveals its age, composition, and even its future. And then there are the planets. Jupiter's magnetosphere, for instance, emits eerie radio waves that, when converted to sound, resemble interstellar whale songs haunting, undulating calls shaped by the planet's swirling magnetic fields. Saturn's rings, too, generate waves of their own, with particles colliding in rhythmic patterns that create subtle vibrations detectable by spacecraft like Cassini. Even Earth's own magnetic field produces a protective chorus of electromagnetic waves, a constant hum against the solar wind. The ancients weren't entirely wrong. There is a music of the spheres, not as a mystical force, but as a physical reality. Every orbit, every rotation, every seismic shudder in a star sends vibrations echoing through space, a cosmic soundtrack we're only now learning to decode. And with missions like ESA's upcoming Plato telescope, designed to study stellar oscillations in unprecedented detail, we're on the verge of hearing the universe's oldest songs clearer than ever before. Deep in the vast, dark reaches between stars, something extraordinary is happening. Clouds of gas so massive they could birth entire solar systems are humming a quiet song. These giant molecular clouds, some spanning hundreds of light years, are the cosmic nurseries where stars are made, and though they seem silent to our ears, their faint radio whispers carry the secrets of creation itself. Picture a cloud so cold and dense, its hydrogen molecules huddled together, vibrating at frequencies just above absolute zero. These vibrations emit weak radio signals so faint they're drowned out by the noise of Earth's own atmosphere. But with radio telescopes like ALMA in Chile's high deserts, scientists can tune into these murmurs. When translated into sound, they become a low, haunting drone, like wind rushing through a canyon. That sound isn't random. It's the signature of gravity's relentless pull, the moment when a cloud's delicate balance tips and it begins collapsing inward, destined to become a star. What's astonishing is how much these sounds reveal. The pitch and rhythm of the radio waves tell us about the cloud's temperature, density, and even its motion. Some clouds hum in smooth, steady tones. These are the stable ones, biding their time. Others crackle with turbulence, their frequencies jagged and chaotic. These are the clouds on the verge of fragmentation, where pockets of gas are knotting into the seeds of future stars. It's like listening to the first breaths of a storm, knowing which gusts will grow into hurricanes. And then there are the echoes of magnetic fields. These invisible forces thread through the clouds like cosmic guitar strings, guiding the flow of gas and slowing its collapse. When scientists map the polarized radio waves, essentially the sound of these fields, they hear something like a deep, resonant hum, layered with higher harmonics. The stronger the field, the tighter the vibrations, shaping how stars will form. Without these magnetic whispers, gas would collapse too fast, birthing stars in a chaotic frenzy instead of the measured, elegant dance we observe. But perhaps the most profound discovery comes from listening to the youngest stars still embedded in their gas cocoons. Their radiation stirs the surrounding molecules, creating feedback loops that sound like rhythmic pulses, nature's way of regulating star formation. Too much feedback and the cloud disperses too soon, too little, and stars would gorge themselves on gas, growing monstrously large. The balance is precise, and it's written in the frequencies we capture. These interstellar murmurs aren't just about distant star factories, they're about us. Every atom in your body, every planet in our solar system, was once part of a cloud like this. By decoding their whispers, we're hearing the opening notes of our own origin story, a song that began billions of years ago and is still playing, if only we know how to listen. Magnetars are the universe's ultimate pressure cookers, neutron stars so volatile. Their very existence defies the laws of physics as we know them. Imagine a cosmic object with the mass of 2 suns crammed into a sphere the size of Manhattan, spinning faster than a blender blade, wrapped in magnetic fields so powerful they could strip the data from every credit card on Earth from halfway across the galaxy. These aren't just strong magnets, they're monsters, and when their magnetic fields twist too far, snapping like overstretched rubber bands, the result is a scream so loud it reverberates across the cosmos. Scientists call these events starquakes, but that word doesn't do them justice. When a magnetar's crust fractures under the strain of its own magnetism, it releases a burst of energy so intense it can outshine our entire Milky Way for a fraction of a second. Convert those bursts into sound and you'd hear something chilling, a sharp, high-pitched screech like metal tearing under unimaginable force. These aren't just random noises. They're distress signals from the edge of reality, where matter is stretched so thin, protons and electrons fuse into exotic strings of quantum soup. What makes these sounds so valuable? They're the only way to study physics at energies a quadrillion times stronger than anything we can create in particle colliders. Every screech carries clues about how magnetic fields warp space-time itself, or how matter behaves when crushed into forms no lab could ever replicate. Take magnetar SGR 1806-20 for example. When it erupted in 2004, its gamma-ray burst was so powerful, it ionized Earth's upper atmosphere from 50,000 light-years away. The vibrations from that event, translated into sound, revealed something shocking. The star's surface might be a solid crystalline lattice, vibrating like a gong struck by the universe's strongest hammer. But the real mystery lies in what these sounds don't tell us. Sometimes magnetars emit softer, rhythmic pulses before a big quake, a cosmic countdown to catastrophe. Other times they fall silent for years, only to erupt without warning. It's as if they're whispering the rules of a game we don't yet understand, one where gravity and magnetism duel for dominance. And with each screech we decode, we're not just listening to a dying star's cry. We're eavesdropping on the universe's most extreme laboratory, where the very fabric of reality is being stress-tested in ways we're only beginning to comprehend. Here's the wildest part. Magnetars might hold the key to one of astronomy's biggest puzzles: fast radio bursts. These mysterious, millisecond-long blasts of radio waves have baffled scientists for years. But recently, some have been traced back to magnetar activity, their signals bearing the same frantic, high-pitched signatures as magnetic snap events. If that connection holds, it means these screaming stars aren't just cosmic oddities. They might be cosmic lighthouses, their distress calls shining a light on the universe's most hidden corners. And as our telescopes grow more sensitive, who knows what other secrets we'll uncover when we really listen to the screams of twisted space itself. Dark matter doesn't just hide in the shadows, it sings. This invisible substance, making up 27% of the universe, doesn't emit light or absorb it. But if we could listen to its gravitational influence, we'd hear something extraordinary. A bass note so deep, it vibrates through the cosmos like the lowest pedal tone of a pipe organ. Scientists call it actinic dark matter noise, a hypothetical hum created by ultra-light particles oscillating across space. Picture standing in a dense fog where every droplet vibrates at a frequency too subtle to hear, yet together they create a resonance so vast it bends the fabric of reality. That's the scale of dark matter's whisper. To simulate this sound, researchers feed hypothetical dark matter models into supercomputers, calculating how these particles would interact with ordinary matter. The result, a droning, almost meditative tone, fluctuating as galaxies rotate and collide. It's not a single pitch but a chorus, shifting slightly as dark matter clumps around galaxies or streams through cosmic voids. Some models even suggest harmonics, like the overtones of a plucked string, revealing how dark matter might cluster at different scales. These simulations aren't just eerie soundscapes. They're experiments in cosmic archaeology, helping us trace how dark matter's gravitational scaffolding shaped everything from the first galaxies to the web-like structure of the modern universe. Here's where it gets even stranger. Dark matter might not hum uniformly. In some theories, certain particles could ring when they interact with magnetic fields or black holes, producing localized chirps or pulses buried in the drone. Others speculate that dark matter vortices, spinning knots of invisible material, might create low-frequency beats, like the rhythmic throb of a subwoofer. These patterns could explain why galaxies rotate faster than visible matter alone should allow, or why some star clusters move as if tugged by unseen currents. The challenge: we've never directly detected dark matter, but sound offers a clever workaround. Just as you can feel a train's rumble before you see it, dark matter's gravitational vibrations leave subtle imprints on visible matter. By studying the precise orbits of stars or the bending of light around galaxies, astronomers reverse engineer the sound waves dark matter would produce. It's like reconstructing a symphony from the vibrations it leaves on a glass of water. And with projects like the future LISA gravitational wave detector, we might soon capture these vibrations directly, listening for the faintest tremors in space-time itself. What if dark matter's hum holds the key to the universe's fate? Its gravitational pull slows cosmic expansion, while dark energy accelerates it. By mapping the tone and distribution of this invisible drone, we could predict whether the universe will end in a cold whisper or a violent crescendo. For now, the sound remains a theoretical ghost, a melody we're still learning to hear. But one day, tuning into dark matter's frequency might not just solve a mystery. It could reveal the universe's hidden rhythm, a beat that's been pulsing since the very beginning. The sun doesn't just shine, it screams. Every second, it blasts 1,000,000 tons of charged particles into space at speeds topping 1,000,000 miles per hour. This torrent, known as the solar wind, isn't silent. As it races past Earth, it sings a haunting chorus of pops, crackles, and hisses trapped in our planet's magnetic grip. Tune into these sounds, and you're hearing the raw voice of space weather, a real-time broadcast of the sun's fury with the power to reshape technology and even human history. The science behind these eerie noises starts with Earth's magnetosphere, a protective bubble of magnetic fields that deflects most of the solar wind. But when those charged particles collide with the magnetosphere's outer edges, they don't just bounce off, they trigger electromagnetic vibrations. Some ripple along magnetic field lines like plucked guitar strings, creating ultra-low frequency waves called whistlers. Others spark bursts of radiostatic as electrons spiral violently toward the poles. When converted to sound, the effect is surreal, a mix of ghostly chimes, staccato clicks, and the white noise hiss of a detuned radio. But these aren't just cosmic sound effects, they're early warnings. The crackling intensity of these noises correlates with solar activity. The louder and more chaotic the sounds, the stronger the solar storm brewing. In 2003, a monstrous solar eruption called the Halloween storms triggered a cacophony of these radio emissions, followed by blackouts in Sweden and damaged satellites. By monitoring this electromagnetic static, scientists can predict when a coronal mass ejection, a sunshot of plasma weighing billions of tons, might slam into Earth, giving power grids and airlines precious hours to prepare. Here's where it gets even wilder. The solar wind doesn't just hit our magnetic field, it shapes it. During intense storms, the magnetosphere compresses like a squeezed balloon, while its tail stretches hundreds of Earth lengths downstream. These distortions create new resonance chambers, altering the pitch and pattern of the sounds. Imagine a colossal organ where solar wind pressure shifts the pipe's length in real time. That's why space weather forecasters don't just listen for volume, they analyze frequency. A sudden drop in pitch might signal a magnetic field buckling under pressure, while rising tones hint at incoming shockwaves. And the solar wind symphony isn't unique to Earth. Around Jupiter, where the magnetic field is 20,000 times stronger, the same interactions produce deeper, thunderous roars, a bass note so powerful it accelerates particles to nearly light speed. Even Mars, with its fractured magnetic remnants, whispers with faint, scattered static where the solar wind leaks through. Each planet's song reveals its magnetic personality, a sonic fingerprint of how worlds guard or fail to guard against the sun's relentless breath. What's next? Projects like NASA, a solar dynamics observatory, and the upcoming ESCAPADE mission to Mars are refining how we translate these space sounds into actionable data. Machine learning now sifts through decades of solar wind recordings, spotting patterns humans might miss. One day, we might have a solar storm alarm as reliable as a tornado siren, all because we learned to listen to the sun's roar. So the next time you hear static on a radio, remember, it might not be interference. It could be the sun whispering or shouting across 93 million miles of void. Exoplanets aren't just silent rocks drifting in the void, they're cosmic tuning forks, vibrating with the echoes of distant storms and winds. Take HD 189733b, a gas giant 60 light-years away, where supersonic winds rip through the atmosphere at 5,000 miles per hour. When scientists modeled the pressure waves generated by these winds, they uncovered something astonishing. The planet sings, not in the way Earth's atmosphere hums with gentle breezes, but in a deep, resonant drone, like the lowest note of a pipe organ stretched across space. These aren't random noises. They're sonic fingerprints, unique vibrations that reveal the planet's atmospheric density, temperature, even the presence of exotic compounds like silicate rain. But how do we hear something so impossibly far away? The secret lies in starlight. As an exoplanet orbits its star, the light filtering through its atmosphere gets subtly altered by molecules in the air. By analyzing these changes, a technique called transmission spectroscopy, researchers can reconstruct the pressure waves moving through the alien skies. Imagine holding a flashlight behind a frosted glass window while someone taps the pane. The way the light flickers tells you about the vibrations. Now scale that up to a planet-sized window, and you've got the blueprint for turning starlight into sound. Some exoplanets take this symphony to extremes. WASP 76b, a scorching world where iron vaporizes on the day side and rains down on the night, generates shock waves that ripple through its atmosphere at Mach speeds. Converted into sound, these waves become a metallic, pulsating roar, a storm of liquid iron screaming across the sky. Then there's GJ1214b, a steamy water world, whose thick, humid air muffles vibrations into a low, diffuse hum, like the sound of a distant ocean trapped under miles of fog. The real prize, though, is what these sounds could tell us about habitability. Earth's atmosphere doesn't just hum, it crackles with the static of lightning, thrums with the pulse of ocean waves, and even carries the faint, rhythmic signatures of life. If an exoplanet's acoustic profile shows similar complexity, seasonal shifts, chaotic weather patterns, or chemical imbalances that hint at photosynthesis, it might be the closest thing we have to hearing a biosphere breathe. Future missions like NASA's Habitable Worlds Observatory aim to do exactly that, using ultra-sensitive instruments to eavesdrop on alien atmospheres like a doctor listening for a heartbeat. But here's the twist: some sounds might be deliberate. If intelligent life exists, they could encode information in atmospheric waves, broadcasting signals across star systems without radios. It's a long shot, but not impossible. After all, we've turned Jupiter's magnetic pulses into music. Why couldn't another civilization do the same? Whether it's the howl of a hydrogen hurricane or the whisper of an oxygen-rich breeze, every exoplanet's voice carries a story. And with every note we decode, we're not just exploring alien worlds. We're learning to listen to the universe's most distant choirs. When a star reaches the end of its life in a cataclysmic supernova, it doesn't fade quietly, it screams. These explosions, some of the most violent events in the universe, unleash shockwaves so powerful, they ripple through the surrounding gas and dust like a sonic boom in slow motion. If we could stand in the vicinity, though we'd be instantly vaporized, the sound would be deafening. A single supernova can outshine an entire galaxy for weeks, and the vibrations it leaves behind are just as extraordinary. The key to understanding these cosmic death cries lies in the elements they create. Inside a dying star's core, temperatures and pressures reach unimaginable extremes, fusing atoms into heavier and heavier elements. When the star finally collapses, the rebound explosion flings these newly forged materials into space at nearly a tenth the speed of light. Gold, platinum, uranium, the very metals that make up your jewelry or power nuclear reactors, were born in these violent last moments. By analyzing the sound of these shockwaves converted from X-ray and radio emissions, scientists can trace how these elements disperse, like listening to the echoes of a cosmic forge. But not all supernovas sound the same. A massive star collapsing in on itself produces a deep, resonant boom, its shock waves expanding symmetrically like a thunderclap in every direction. Meanwhile, a white dwarf stealing matter from a companion star detonates in a sharper, more chaotic burst. Think of the difference between a bass drum and a snare. These acoustic fingerprints reveal not just how the star died, but how it lived. The pitch and decay of the shockwaves hint at the star's original size, its chemical makeup, even the turbulence of its final moments. One of the most haunting examples comes from Cassiopeia A, the remnant of a supernova that lit up Earth's skies around 300 years ago. When astronomers translated its expanding debris field into sound, they heard something eerie, a layered, almost mournful wail, with higher frequency vibrations skittering ahead of the deeper tones. That's because the explosion wasn't perfectly even. Some material raced outward faster, creating a dissonance in the shock waves. It's like hearing the star's death throes in surround sound, each note a clue to its violent demise. Here's what's even wilder. These sounds don't just fade into silence. Supernova remnants can keep ringing for centuries, their shockwaves bouncing off interstellar clouds and creating interference patterns. By studying these echoes, researchers have discovered something astonishing. Some elements aren't just flung outward. They're recycled, swept up in new shockwaves and hurled even farther, seeding future generations of stars and planets. So the next time you look up at the night sky, remember, those silent points of light have voices, and when they finally speak, it's with the force of a universe rewriting itself. Each supernova's cry is a cosmic ingredient list, a recipe for everything from the iron in your blood to the silicon in your phone. We're not just observers of these explosions. We're made from them. Einstein's theory of relativity gave us a radical idea. Space isn't just an empty stage where cosmic events unfold. It's a dynamic fabric, stretching and bending under the weight of massive objects. And when those objects move violently, like black holes colliding or neutron stars spiraling into each other, they send shockwaves rippling through space-time itself. These are gravitational waves, the universe's most elusive vibrations. For decades, they existed only as equations on paper. Then, in 2015, humanity heard them for the first time, a faint, fleeting chirp, lasting less than a second, captured by the Laser Interferometer Gravitational Wave Observatory, or LIGO. That sound marked the dawn of a new era in astronomy. What does a gravitational wave actually sound like? Imagine plucking a guitar string so massive, it's light years long. The resulting tone would be far too low for human ears to hear. But when LIGO scientists shifted the frequency into our range, the signal became a quick, upward sweep, a cosmic whoop that starts as a murmur and rises to a sudden crescendo. That's the sound of two black holes, each dozens of times heavier than the Sun, whirling around each other hundreds of times per second before merging in a final, universe-shaking collision. The pitch of the chirp reveals their masses. The timing tells us how far away they are. It's like listening to a fingerprint of gravity itself. But LIGO doesn't work like a traditional telescope. Instead of collecting light, it measures the subtle stretching and squeezing of space-time using laser beams traveling down 4-kilometer-long tunnels. When a gravitational wave passes through Earth, it briefly warps the distance between mirrors at the ends of those tunnels by less than 1,000th the width of a proton. That's the equivalent of measuring the distance to the nearest star and noticing if it changes by the thickness of a human hair. The precision is staggering, and the rewards are even greater. Every chirp LIGO detects is a snapshot of the universe's most extreme environments, places where time slows down, space twists like taffy, and matter is crushed into oblivion. Some gravitational waves tell stories we never expected. In 2017, LIGO and its European counterpart, Virgo, detected a neutron star collision. Unlike black hole mergers, this event didn't end in silence. It erupted in light gamma rays, X-rays, even a glow visible to amateur telescopes. The sound of the waves, combined with the flash, confirmed a theory decades in the making. These collisions forge heavy elements like gold and platinum. That single detection answered two mysteries at once: how gravitational waves travel through space and where the universe's precious metals come from. Now, scientists are tuning into even stranger signals. Some waves ring like muffled bells, hinting at black holes with bizarre shapes or exotic stars made of quark matter. Others arrive in quick succession, suggesting mergers happen far more often than we thought. And with new detectors like the space-based LISA mission planned for the 2030s, we'll soon hear frequencies too low for Earth-bound instruments, the rumbles of supermassive black holes dancing at the centers of galaxies. Gravitational waves aren't just another way to observe the cosmos. They're a language, a direct line to the universe's most violent, hidden moments. Every chirp is a message from the warped edges of reality, whispering secrets about how space, time, and matter behave under conditions we can't possibly recreate. And as our ears grow sharper, we're not just listening to the universe anymore. We're decoding its deepest, most fundamental rhythms. The first few microseconds after the Big Bang weren't silent. They were a roaring chaos of energy, a plasma so dense and hot, light couldn't even travel through it. But trapped inside that primordial soup were sound waves, ripples of pressure moving at more than half the speed of light. These weren't ordinary vibrations. They were the universe's first notes, a cosmic symphony that set the stage for everything that followed. Today, we can actually recreate those sounds not with microphones, but with supercomputers and equations, transforming ancient echoes into something we can hear. And what they reveal is astonishing. These primordial hums sculpted the very structure of the cosmos, from the largest galaxy clusters to the voids between them. Picture the early universe as a pot of water just before it boils, bubbles of energy forming, colliding, and popping in a frenzied dance. As the cosmos expanded and cooled, those bubbles left behind faint imprints in the plasma, regions where matter was slightly denser or sparser. These ripples became standing waves, oscillating through the infant universe like the vibrations of a struck bell. The frequencies weren't random. They followed precise patterns dictated by the physics of the Big Bang, with peaks and troughs spaced at intervals that still echo in the cosmic microwave background today. When scientists simulate these sounds, they uncover something extraordinary: the universe's original volume. The loudest notes, waves with the highest amplitude, correspond to the most massive structures in the modern cosmos, like the Great Wall of galaxies. Quieter harmonics trace the delicate filaments connecting them. It's as if the universe was tuning an instrument, setting the scale for everything that would come. Some models even suggest these sounds could help test cosmic inflation, the theory that the universe underwent a rapid, exponential expansion in its first fraction of a second. If inflation happened, it would have stretched certain sound waves to impossibly low frequencies, leaving behind a signature we might one day detect in gravitational waves or the polarization of the CMB. But here's the most mind-bending part. Those primordial sounds didn't just shape the universe, they are the universe. Every galaxy, every star, every atom in your body traces back to those early density fluctuations. The rhythm of those waves determined where matter clumped together and where it stayed sparse, guiding the formation of the cosmic web we see today. It's like listening to a recording of your own birth, a sonic blueprint of existence itself. And as our simulations grow more precise, we're not just hearing the past, we're deciphering the universe's deepest grammar, the hidden rules written in vibrations older than time. Beneath the smooth expanse of space-time lies a hidden chaos, a seething, frothing ocean of energy where reality itself flickers in and out of existence. This is quantum foam, the universe's smallest and most turbulent scale, where particles and forces dance in a frenzy so brief it defies measurement. If you could listen closely enough far beyond the limits of current technology, you might hear it as a faint, crackling static, the background hiss of creation and annihilation playing on an endless loop. These quantum fluctuations aren't random. They're the echoes of a fundamental truth: empty space is never truly empty. At scales a trillion times smaller than an atom, virtual particles pop into existence for mere fractions of a second, borrowing energy from the universe before vanishing again. It's as if space-time itself is a stormy sea, with waves so tiny, they're invisible to all but the most precise theoretical models. Yet these ripples might hold the key to one of physics' greatest mysteries: quantum gravity, the elusive theory that could unite Einstein's relativity with the bizarre rules of the quantum world. Imagine tuning a radio to a frequency between stations, where the static isn't just noise but a signal from the fabric of reality. That's the dream behind experiments like the proposed quantum microphone, a device sensitive enough to detect the faint vibrations of space-time's foam. While we're decades away from building such an instrument, the math suggests what we might hear: a low, uneven crackle, like the sound of distant radio interference or the fizz of carbonation in a glass. Each pop and hiss would represent a fluctuation where gravity and quantum mechanics collide, revealing how space-time behaves at energies so high they've only existed once, during the Big Bang itself. Some theories go even further. In certain models of quantum gravity, space-time isn't just foamy, it's fractal, with structures repeating at smaller and smaller scales like a cosmic hall of mirrors. The sound of this fractal foam wouldn't be uniform static but a layered chorus, with higher-pitched frequencies nested inside deeper drones. It's a sonic fingerprint that could distinguish between competing theories, like loop quantum gravity or string theory, by the patterns it leaves in the noise. But why chase such an ephemeral signal? Because quantum foam isn't just academic curiosity. It's the frontier where our understanding of reality breaks down. Black holes, for instance, might churn the foam at their event horizons, creating a buzzing threshold between existence and oblivion. Wormholes, if they exist, could be stabilized by these fluctuations, their throats humming with quantum static. Even the expansion of the universe might leave traces in the foam's vibrations, like grooves in a cosmic record. For now, the static remains theoretical, a whisper just beyond our hearing. But as sensors grow more precise and experiments more ambitious, we might one day tune into the universe's foundational noise, and when we do, we won't just be listening to the quantum foam. We'll be eavesdropping on the very code of reality, written in frequencies so small they've been waiting since the dawn of time to be heard. For nearly 60 years, scientists have been scanning the skies for something extraordinary, a signal that doesn't belong. Not the natural hum of pulsars or the crackle of cosmic dust, but a deliberate broadcast, a message crafted by intelligence beyond Earth. This is the mission of SETI, the search for extraterrestrial intelligence, an effort to eavesdrop on the universe's potential conversations. The tools, massive radio telescopes trained on distant stars, listening for patterns that defy natural explanation. A single, unnatural pulse buried in the static could change everything. Think about how we communicate here on Earth. Radio waves carry our broadcasts, our music, even our early television signals, all leaking into space, drifting outward at the speed of light. SETI operates on the assumption that another civilization might do the same, but searching isn't as simple as tuning into an alien radio station. The cosmos is vast, and signals weaken over distance, drowned out by the noise of stars, galaxies, and the cosmic microwave background. To find a transmission, scientists don't just listen, they hunt for anomalies. A narrow-band signal, for instance, one that clings to a specific frequency with unnatural precision, would stand out like a spotlight in a fog. Or a repeating pattern, a mathematical sequence embedded in the noise, something nature wouldn't produce by chance. One of the most tantalizing moments in this search came in 1977, when Ohio State University's Big Ear telescope picked up a signal so unusual, an astronomer famously scribbled, "Wow." Next to the data printout, lasting 72 seconds, the signal was 30 times stronger than the background noise and matched the expected signature of an artificial transmission. But despite repeated attempts, it was never heard again. Was it a passing satellite, a glitch, or something far more profound? The mystery remains, a ghost in the static that keeps the search alive. Modern SETI has evolved far beyond those early efforts. Projects like Breakthrough Listen harness the power of artificial intelligence, sifting through millions of radio channels simultaneously, analyzing data faster than any human could. Telescopes like the Allen Telescope array scan thousands of star systems at once, while new approaches look for laser pulses or even technosignatures, hints of alien megastructures or atmospheric pollution that might betray a technological civilization. The search has expanded beyond radio because who's to say an advanced species would communicate the way we do? But here's the haunting question: what if we're not listening the right way? Imagine an alien civilization encoding messages in neutrinos or manipulating quantum entanglement for instant communication across light years. Our current tools might miss it entirely. Or worse, what if the signals are all around us, hidden in plain sight, waiting for us to develop the right decoder? Some researchers suggest looking for benign beacons, deliberate signals designed to be universal, like a cosmic SOS or a primer on the laws of physics. Others propose that advanced civilizations might leave message bottles, data stored in pulsars, or even the structure of space-time itself. If we ever do detect a confirmed signal, the implications would be staggering. It wouldn't just answer whether we're alone, it would redefine our place in the cosmos. A single message, even if we couldn't decipher it, would prove that intelligence isn't a fluke, that the universe hums with more than just natural noise. And perhaps, just perhaps, it would carry a lesson that out there in the great dark, someone else is listening too. Jupiter doesn't just have a magnetic field, it has a voice. The largest planet in our solar system belts out an eerie chorus of whistles, clicks, and pops, a symphony of electromagnetic noise generated by charged particles spiraling along its colossal magnetic field lines. Recorded by spacecraft like Voyager and Juno, these sounds aren't random static. They're the heartbeat of a planetary giant, a sonic fingerprint revealing secrets about Jupiter's storm-racked atmosphere, its radiation belts, and even its hidden oceans. Picture the scene: electrons and ions ripped from Jupiter's volcanic moon Io get caught in the planet's magnetic grip, a field 20,000 times stronger than Earth's. As these particles whip around at near light speeds, they generate intense radio emissions, some so low frequency they'd rumble far below human hearing. But when shifted into our auditory range, the result is haunting. Whistlers' rising tones like a theremin's glide leap out of the noise created by lightning strikes deep in Jupiter's clouds. Meanwhile, chorus waves' sharp, chirping bursts echo like a flock of cosmic birds, produced by electrons oscillating in the magnetosphere. These sounds aren't just atmospheric byproducts. They're a live feed of Jupiter's invisible forces, a real-time map of how energy surges through its space environment. The magic happens when these waves interact with Jupiter's moons. Europa, with its subsurface ocean, plows through the planet's magnetic field, creating turbulence that alters the chorus in detectable ways. Listen closely, and you might hear the subtle shifts in pitch and static that hint at the moon's hidden waters. Ganymede, the solar system's only moon with its own magnetic field, duets with Jupiter's emissions, producing interference patterns that reveal its internal structure. Even Eo's volcanic eruptions leave acoustic traces, as charged sulfur and oxygen ions vomited into space get swept up in Jupiter's rotation, adding crackling harmonics to the mix. What's truly surprising is how this electromagnetic song affects us here on Earth. Jupiter's radiation belts are the most violent in the solar system, a lethal zone where unshielded electronics would fry in seconds. By decoding the chorus, scientists learn how particles accelerate in such extreme environments, knowledge that protects satellites and future astronauts. Some emissions even reach Earth as very low-frequency radio waves, detectable by ham radio operators as eerie, Jovian bursts bleeding through their receivers. But the grandest revelation might still be coming. NASA Juno spacecraft, orbiting Jupiter since 2016, has captured chorus waves with unprecedented clarity. Some recordings sound like dolphins chattering underwater, others like a crackling campfire. Each noise corresponds to a specific interaction: solar wind buffeting the magnetosphere, plasma waves resonating in new patterns, even hints of charged particles raining down near Jupiter's poles. It's as if the planet is whispering its secrets in a language we're only now learning to speak. And with every chirp and whistle, Jupiter reminds us the universe isn't just something we see. It's something we hear. Saturn's rings aren't just a breathtaking sight, they're a cosmic sound system, crackling with radio waves as countless icy particles collide and swirl around the planet. When NASA Cassini spacecraft dipped close to the rings, its instruments picked up these emissions and translated them into sound. The result, a symphony of pops and hisses, like the static of a vintage vinyl record playing the universe's most mysterious album. But these aren't random noises. Each crackle carries clues about the rings' hidden structure, how thick they are, what they're made of, even how they interact with Saturn's magnetic field. The secret lies in the collisions themselves. Picture trillions of ice fragments, some as small as grains of sand, others as large as houses, all orbiting Saturn at different speeds. When these particles bump into each other, the energy of the impact generates plasma waves, ripples of charged particles that Cassini's radio antenna could detect. The denser the region of rings, the more frequent the collisions, creating a louder, more chaotic static. In the gaps between rings where particles are sparse, the noise drops to a faint whisper. It's like running a needle over a record's grooves, hearing the music rise and fall with the depth of each track. What's truly fascinating is how these sounds change depending on where Cassini listened. Near the planet, the radio emissions took on a lower, thunderous tone, reflecting the influence of Saturn's powerful magnetic field. Farther out, where the rings are thinner and more delicate, the static became sharper, almost metallic, like the sound of hail hitting a tin roof. Scientists even discovered that certain ring features, like the ghostly spokes that appear and vanish, left distinct acoustic fingerprints, sudden bursts of noise amid the usual crackle. But the rings aren't just talking to us, they're singing to Saturn itself. The planet's magnetic field funnels some of these radio waves toward its poles, where they interact with the atmosphere, creating eerie auroras. It's a feedback loop of sound and light, a celestial conversation between planet and rings that's been ongoing for millions of years. And just like a record's scratches tell the story of how often it's been played, these emissions hint at the ring's age and evolution. Some researchers believe the constant collisions are grinding the rings down, slowly turning them into dust, meaning one day, Saturn's iconic soundtrack could fade to silence. For now, though, the rings keep spinning, their particles dancing to a rhythm older than human history. Every pop and hiss is a reminder that even in the stillness of space, nothing is truly silent. The universe is always vibrating, always humming, and sometimes, if we listen closely enough, it lets us in on the music. Comets don't just streak silently across the sky, they sing. When the European Space Agency's Rosetta spacecraft arrived at Comet 67P in 2014, its instruments picked up something unexpected, a bizarre, crackling melody emanating from the comet's ion tail. This wasn't the sound of ice cracking or dust scattering. It was the voice of the solar wind itself, a stream of charged particles from the sun colliding with the comet's electrified gases. Translated into sound waves, these interactions became a chorus of pops and whistles, like radio static mixed with the eerie creaks of an old wooden ship. But this noise wasn't just cosmic ambience. It was a direct line into the chemistry of one of the solar system's most mysterious travelers. Here's how it works. As a comet nears the sun, heat vaporizes its icy surface, releasing gas and dust into space. But the sun doesn't just warm the comet, it charges it. Ultraviolet light strips electrons from these gases, turning them into ions, which then get caught in the solar wind's magnetic grip. The result, a tail that doesn't just stream behind the comet but vibrates, resonating with the solar wind's fluctuations like a tuning fork struck by a storm. Rosetta's Plasma Consortium instruments detected these oscillations as rhythmic waves, their frequencies shifting as the solar wind's intensity ebbed and flowed. When scientists sped up the data into audible range, the comet's song emerged, a haunting, ever-changing soundtrack to its journey around the sun. What's wild is how much these sounds reveal. The pitch and amplitude of the crackles correspond to the comet's ion composition. Water vapor, carbon dioxide, even organic molecules like formaldehyde. Each gas interacts with the solar wind at distinct frequencies, creating a sonic fingerprint of the comet's makeup. At 67P, the dominant tones hinted at vast amounts of carbon monoxide, a volatile ice that vaporizes far from the sun, explaining why this comet was so active even in the colder reaches of its orbit. Other fluctuations matched bursts of dust erupting from the surface, each plume adding a staccato click to the symphony. It's like listening to a chemical recipe being written in real time, one that might have seeded young planets with the ingredients for life. But the real surprise was how the comet's song changed as it moved. During solar storms, when the sun hurled especially fierce gusts of charged particles, the crackling intensified into a roar, the ions in the tail vibrating like plucked strings. When Rosetta flew through the tail itself, the static became a chaotic jumble, revealing turbulence and eddies in the ionized gas, structures invisible to cameras but unmistakable in sound. Even the comet's irregular shape played a role, its twin-lobed rubber duck form creating asymmetries in the emissions, as if the music was echoing through a cosmic canyon. Why does this matter? Because comets are time capsules, icy relics from the solar system's birth. Their sounds carry echoes of that ancient era when the planets were still forming and the solar wind was a newborn gale. By decoding the crackles and whistles of 67P, scientists aren't just studying a single comet. They're hearing the voice of the early solar system, a whisper from a time when Earth itself was just a swirl of dust and gas. And with every mission that listens to these cosmic minstrels, we're one step closer to understanding the soundtrack of our own origins. Interstellar dust might seem like silent, insignificant specks floating in the void, but listen closely and you'll hear the faintest rustle of the cosmos. These microscopic grains, no larger than a fraction of a human hair, are constantly bombarded by charged particles from stars and cosmic rays. When these particles strike the dust, they don't just bounce off, they generate tiny bursts of radio waves, a subtle crackling that scientists can detect and translate into sound. It's like hearing the soft patter of rain on a roof, except this rain has been falling for billions of years, carrying secrets about the invisible scaffolding of our galaxy. Each of these whispers tells a story. The pitch and intensity of the radio emissions reveal the dust's composition, whether it's made of carbon, silicates, or even organic molecules. The way the sound scatters and fades hints at the dust's temperature and density, painting a sonic map of regions too dark for telescopes to see. In the spiral arms of the Milky Way, where dust gathers in thick clouds, the crackling grows louder, a chorus of collisions marking the birthplaces of future stars. In the emptier voids between arms, the noise drops to a murmur, a hush that speaks of vast, lonely stretches where matter is sparse. But this isn't just about mapping what's there. The sounds of interstellar dust also expose what's missing. Some regions should be dense with dust based on visual observations, yet they're eerily quiet, suggesting hidden forces, like shock waves from supernova or the pull of dark matter, have swept the area clean. Other patches crackle with unexpected intensity, pointing to pockets of dust laced with rare minerals or frozen gases. It's as if the universe left behind a trail of breadcrumbs in radio static, and by following them, we're uncovering the hidden pathways matter takes as it drifts through space. What's truly astonishing is how these tiny grains connect to the grandest scales. The same dust that whispers in radio waves also shapes the light from distant stars, reddening it like a sunset filtered through smoke. When we listen to these emissions, we're not just hearing debris, we're eavesdropping on the raw materials of planets, comets, and even life itself. Every atom in your body once passed through such clouds, buffeted by cosmic winds until gravity pulled it into a star, a planet, and eventually you. So the next time you look up at the night sky, remember, the darkness isn't empty. It's alive with the soft, ceaseless rustle of dust writing the next chapter of the universe's story. At the heart of nearly every galaxy, there's a gravitational monster lurking, a supermassive black hole millions or even billions of times heavier than our sun. These cosmic behemoths don't just sit quietly. They devour matter with such violence, they launch jets of plasma at nearly light speed, stretching thousands of light years into space. But here's what's truly astonishing: those jets don't just stream outward. They vibrate, sending shockwaves rippling through the surrounding gas like a bell struck by a hammer. These aren't fleeting echoes, they're cosmic reverberations lasting millions of years, carrying clues about how black holes shape the galaxies they call home. Take the supermassive black hole in galaxy M87, for example. When the Event Horizon Telescope captured its now famous image, scientists noticed something hidden in the data. The black hole's jets weren't smooth. They had subtle kinks and bends, like a garden hose with water pulsing through it. These distortions weren't random. They were standing waves, oscillations caused by the black hole's spin warping the fabric of space-time around it. Imagine twirling a spoon in honey. The slower, thicker rotations create ripples that linger far longer than in water. That's exactly what's happening here, except on a scale so vast. The honey is interstellar gas, and the ripples take millennia to fade. What's even wilder is how these vibrations influence entire galaxies. As the jets plow through surrounding gas clouds, their oscillations trigger chain reactions. Regions of compressed gas heat up, sparking new star formation, while rarefied zones become stellar deserts. The echoes essentially sculpt their host galaxies over cosmic time, determining where stars can form and where they can't. In galaxy NGC 1265, astronomers have traced these echoes back through radio emissions, uncovering a pattern of star clusters aligned like pearls on a string, each one marking where a jet's pressure wave squeezed the gas just enough to ignite stellar birth. But the most profound discovery comes from listening to these echoes across different galaxies. Some supermassive black holes hum in deep, resonant tones, their jets vibrating slowly, a sign they're well-fed and spinning steadily. Others emit erratic, staccato bursts, suggesting they're starved of matter, lurching unpredictably as they consume whatever stray gas drifts too close. These acoustic fingerprints reveal more than just a black hole's appetite. They tell us about its history, whether it grew through steady meals or violent mergers, and how those growth spurts affected its galactic neighborhood. Here's the twist: sometimes the echoes outlive the jets themselves. In Galaxy Cluster MS0735, astronomers found vast cavities in the hot gas, bubbles carved by ancient jets that shut off millions of years ago. Yet the gas at their edges still ripples, like the surface of a pond long after the stone has sunk. These ghostly vibrations let us peer into the past, reconstructing the outbursts of black holes that flared bright when dinosaurs still walked Earth. It's a reminder that in the cosmos, nothing truly disappears. Energy echoes, movements linger, and if we know how to listen, even the faintest tremors can tell the story of how giants shaped the universe. The center of the Milky Way isn't the serene, star-studded vista we see in photographs. It's a roaring arena of cosmic noise, a maelstrom of radio waves crashing together in a symphony of chaos. At the heart of it all sits Sagittarius A, our galaxy's supermassive black hole, 4 million times the mass of the Sun. But it's not silent. It's surrounded by a swirling disk of superheated gas, a storm of particles spiraling toward oblivion, screaming their final moments across the electromagnetic spectrum. When scientists translate these emissions into sound, the result is anything but peaceful. It's a thunderous, layered drone, punctuated by sharp crackles and sudden bursts like standing in the middle of a celestial hurricane. Every element in this chaotic chorus has a story to tell. The stars orbiting Sagittarius are at breakneck speeds. Some completing a full loop in just a few Earth years emit their own radio signatures, high-pitched whines that rise and fall as they whip past the black hole's event horizon. The gas clouds, stretched and shredded by tidal forces, add a hissing static, their molecules ionized and frantic. And then there are the mysterious, fleeting flares, bursts of energy that erupt without warning, turning the drone into a screeching crescendo for hours or days before fading back into the rumble. These aren't random disturbances, they're clues, hints about how black holes feed, how they interact with their surroundings, and what happens to matter in the most extreme gravitational environment imaginable. What's truly remarkable is how much structure hides in the noise. By isolating specific frequencies, astronomers have uncovered patterns, rhythmic pulses that suggest Sagittarius isn't just a passive monster. It might be choking on its meals, swallowing gas in fits and starts, creating a stuttering rhythm in the radio emissions. Other fluctuations hint at magnetic fields twisting and snapping like rubber bands, releasing energy in waves that ripple through the surrounding plasma. It's as if the black hole is drumming its fingers on the fabric of space-time, and every tap sends vibrations echoing through the galaxy. But the cacophony isn't just coming from Sagittarius A. The region around it, known as the Central Molecular Zone, is a factory of star formation and destruction. Massive young stars blast ultraviolet radiation into nearby gas clouds, ionizing them into glowing, shrieking beacons. Supernova remnants add their own static, the ghosts of dead stars still crackling with energy. Even the dust plays a part, its microscopic grains emitting faint, rustling whispers as they're bombarded by cosmic rays. Together, these sounds paint a portrait of a place where chaos and creation collide, where the laws of physics are pushed to their limits, and where every frequency holds a piece of the Milky Way's origin story. Listening to the galactic center isn't just about cataloging noise. It's about decoding the language of gravity, magnetism, and time. Each burst, each hum, each eerie silence is a message from a realm where space curves into itself and matter vanishes into the abyss. And as our telescopes grow more sensitive, we're not just hearing the chaos, we're starting to understand the music hidden within it. Cosmic strings might sound like science fiction, but they could be the universe's most bizarre musical instruments. Imagine spacetime itself, the fabric of reality, not as a smooth, unbroken sheet, but as a tangled web with flaws, tiny cracks left over from the Big Bang's explosive birth. These defects, known as cosmic strings, would be unimaginably thin yet staggeringly dense, with a single inch weighing more than Mount Everest. And just like a plucked guitar string, they might vibrate, sending tremors through the cosmos at frequencies so low, one full oscillation could take centuries. If these strings exist, their vibrations wouldn't produce ordinary sound. Instead, they'd warp spacetime itself, creating gravitational waves, ripples in the fabric of reality. Unlike the sharp chirps of colliding black holes, cosmic strings would hum with a steady, droning tone, a bass note so deep it's felt more than heard. Some models suggest these strings could even form loops, spinning at near light speed and emitting rhythmic pulses, like a metronome ticking across the ages. The pitch of these waves would reveal the string's tension, a property tied directly to the energy of the early universe. It's as if the cosmos left behind a tuning fork from its infancy, and we're just now learning to listen. Why hunt for such an elusive signal? Because cosmic strings aren't just cosmic curiosities, they're potential keys to physics beyond Einstein. Some theories, like string theory, predict these defects should exist, vibrating in higher dimensions we can't perceive. Others suggest they could be the source of mysterious fast radio bursts or even the seeds for supermassive black holes. Detecting their gravitational hum would be like finding a fossil from the universe's first trillionth of a second, a time when the laws of physics as we know them were still being forged. The challenge is tuning our instruments to the right frequency. Current gravitational wave detectors like LIGO are built to catch the high-frequency crashes of black holes, not the slow, resonant thrum of cosmic strings. But future observatories, like the space-based LISA mission or Pulsar timing arrays, which use the precise ticks of neutron stars as interstellar microphones, could be sensitive enough to pick up these space-time twangs. It's a needle in a haystack search, but if successful, the payoff would be extraordinary. Proof that the universe isn't just expanding, it's singing in a voice older than time. What's tantalizing is how these strings might shape the cosmos even today. As they oscillate, they could slice through galaxies like invisible wires, leaving behind wakes of stars or triggering bursts of star formation. Some researchers speculate that certain oddities in the cosmic microwave background, those faint temperature variations from the Big Bang's afterglow, might bear the scars of ancient strings brushing past. Others wonder if dark matter's mysterious distribution could be traced back to these defects, their gravitational echoes herding particles into the cosmic web we see today. For now, cosmic strings remain theoretical, a ghostly melody waiting to be confirmed. But if we ever do catch their whisper, it won't just be a scientific breakthrough. It'll be a reminder that the universe isn't just a place of silence and darkness. It's a symphony of vibrations, from the smallest quantum tremors to the deepest space-time twangs, all playing a song we're only beginning to understand. The universe isn't just getting bigger, it's humming a note so low it's been playing since the dawn of time. Every galaxy, every star, even the empty stretches between them are being pulled apart by the relentless force of cosmic expansion, stretching the very fabric of space. And just like the pitch of a passing ambulance siren drops as it moves away, the light from distant galaxies gets stretched too shifted toward redder, lower frequencies. But here's the twist. When scientists convert that redshift into sound, the universe's growth isn't silent. It's a deepening, resonant drone, a single tone that drops ever lower as space stretches thinner and galaxies race farther apart. This cosmic hum isn't just an eerie soundtrack, it's one of our most powerful tools for measuring the universe's expansion. The pitch of the drone corresponds directly to how fast a galaxy is receding from us, with lower tones indicating greater distances. By comparing these sonic fingerprints across billions of light years, cosmologists have uncovered something startling. The universe isn't just expanding. It's accelerating, pushed apart by an invisible force we call dark energy. The drone's drop in pitch isn't smooth and steady like a fading echo. It's speeding up as if some unseen hand is turning a cosmic volume knob to warp speed. What's wild is how much this sonic map reveals. In regions where dark energy dominates, the drone plummets into subsonic depths, a rumbling bass that vibrates through the cosmic web. Near galaxy clusters where gravity still fights back, the tone wavers slightly, a subtle fluctuation in the noise that hints at the tug of war between attraction and repulsion. Even the silences tell a story, vast cosmic voids where the drone fades to near inaudibility, their emptiness stretching the limits of what sound can capture. But the real magic happens when we listen to this drone across time. Light from the earliest galaxies, emitted when the universe was a fraction of its current size, reaches us as an ultra-low growl, its original high frequencies stretched beyond recognition. Compare that to younger galaxies whose tones haven't dropped as far, and you get a timeline of cosmic expansion, a sonic fossil record of how space itself has evolved. It's like hearing a recording of the universe aging, its voice deepening with every passing billion years. Yet the most profound insight comes from what we can't hear. The drone's accelerating drop suggests dark energy isn't just a constant force, it might be growing stronger, its influence swelling as the universe ages. If that's true, the drone's final note won't be a fade out, but a catastrophic silence as galaxies vanish over the horizon of perception, their light stretched into wavelengths too long to detect. For now, though, the hum plays on, a bass line to the cosmos that's still writing its own crescendo, and by tuning into its frequency, we're not just measuring the universe's growth. We're listening to the soundtrack of its fate. White dwarfs are the universe's quietest storytellers, the fading embers of stars that once burned bright like our sun. When a star like ours exhausts its nuclear fuel, it doesn't vanish in a blaze of glory. Instead, it sheds its outer layers in a delicate planetary nebula, leaving behind a dense, Earth-sized core that glows with residual heat. This is the white dwarf stage, where a star's afterlife begins as a slow, billion-year cooling process. And just like a piece of iron pulled from a forge gradually loses its glow, these stellar corpses radiate heat in ever-dimming whispers, faint thermal emissions that, when translated into sound, become a haunting, descending tone, a cosmic lullaby for a life that once was. The sound of a white dwarf isn't dramatic. It lacks the explosive crackle of a supernova or the deep hum of a black hole's accretion disk. Instead, it's a soft, almost melancholic hiss, like steam escaping a cooling kettle. This sound comes from the star's thermal radiation. Light waves shifted down the spectrum into longer, redder wavelengths as the object cools. Convert those wavelengths into frequencies within human hearing range, and you get a tone that drops imperceptibly over millennia, mirroring the star's temperature decline. The pitch is directly tied to its energy output. Younger, hotter white dwarfs emit higher frequencies, while ancient, cooler ones drone at depths nearing the threshold of silence. But these fading tones aren't just cosmic background noise, they're clocks, because white dwarfs cool at predictable rates. Their thermal soundtrack allows astronomers to estimate their age, and by extension, the age of the galaxy around them. A white dwarf radiating at 10,000 degrees Kelvin might produce a tone resembling a high flute note, while one cooled to 4,000 degrees would emit a low, cello-like drone. By cataloging these sounds across the Milky Way, scientists have uncovered populations of white dwarfs dating back nearly as far as the universe itself, some over 10 billion years old. Their whispers are time capsules, preserving acoustic snapshots of the galaxy's earliest stellar generations. What's truly remarkable is how these sounds reveal composition. A white dwarf's atmosphere, often helium or hydrogen left over from its star days, absorbs specific wavelengths of light, creating gaps in its thermal emission spectrum. When converted to sound, these gaps appear as missing harmonics, like a piano missing certain keys. By analyzing these acoustic fingerprints, researchers can determine what elements the white dwarf is made of, how its atmosphere interacts with its core, and even whether it's cannibalizing planetary debris from its former solar system. Some white dwarfs emit metallic clinks in their spectra, evidence of heavy elements like iron or silicon sinking through their ultra-dense interiors, a process that distorts their thermal hum like a stone dropped into a pond. Then there are the binary systems, where two white dwarfs orbit each other in a silent dance. As they spiral closer over millennia, their mutual gravity creates ripples in space-time gravitational waves that will eventually merge them. But long before that collision, their thermal emissions intertwine acoustically. Imagine two tuning forks vibrating at slightly different pitches, their tones occasionally sinking into eerie, beating harmonies. These patterns allow astronomers to predict mergers that won't happen for billions of years, events that could reignite nuclear fusion, creating rare zombie stars or even triggering supernova. The quietest white dwarfs, though, hold the most profound lesson. After trillions of years, long after all stars have burned out and galaxies have dimmed, the last white dwarfs will fade to black, their thermal hums finally ceasing. They'll become black dwarfs, cold, dark remnants radiating no light, no heat, no sound. For now, though, their gentle whispers remind us that even in death, stars don't go silently. They linger, telling their stories in frequencies so faint, we must bend the limits of technology to hear them. And in their quiet, we find a humbling truth. The universe doesn't just shout its drama in supernova and quasar jets. Sometimes its most enduring tales are told in a whisper. Neutrinos are the universe's most elusive ghosts. Trillions pass through your body every second, leaving no trace, like whispers in a hurricane. These nearly massless particles, born in the nuclear furnaces of stars and the cataclysmic explosions of supernova, rarely stop to interact with matter. But when they do, the result isn't a grand collision or a flash of light. It's a tiny, almost imperceptible click, a sound so faint it takes mountains of ice or tanks of liquid to hear it. Yet these minuscule signals are anything but insignificant. They're direct messages from the heart of the sun, the remnants of dying stars, and even the violent cores of distant galaxies. To catch a neutrino's whisper, scientists build detectors in some of the most isolated places on Earth, deep underground beneath Antarctic ice, or submerged in abandoned mines. These locations shield experiments from cosmic noise, creating silent arenas where even the softest particle interactions can't hide. Take the Super Kamiok and detector in Japan, a colossal tank filled with 50,000 tons of ultra-pure water. When a neutrino finally bumps into an atom in that water, it releases a flash of light so brief, it's over in a billionth of a second. Sensors lining the walls convert that flash into an electrical pulse, a sharp, digital click that echoes through the data. Multiply those clicks over years of observation, and patterns emerge. The steady rhythm of solar neutrinos, proof that the sun's core is fusing hydrogen into helium right on schedule, or the sudden crescendo of a supernova's neutrino burst, like a distant scream from a star's final moments. What's astonishing is how much these sounds reveal. Solar neutrinos, for instance, arrive in flavors electron, muon, and tau, each corresponding to different nuclear processes. By counting the clicks of each type, physicists confirmed something bizarre. Neutrinos oscillate, morphing from one flavor to another as they travel. This discovery upended decades of assumptions, proving these particles have mass, however minuscule. Then there are the high-energy neutrinos from beyond our galaxy, detected by instruments like IceCube at the South Pole. Their clicks arrive with a force that suggests origins in black hole jets or colliding neutron stars, cosmic accelerators flinging particles across space with energies 1,000,000 times greater than any man-made machine. But the most haunting neutrino symphony came from supernova 1987A. When that star exploded in the Large Magellanic Cloud, detectors on Earth picked up 24 clicks in 13 seconds, a neutrino pulse matching the star's death throes. Those sounds weren't just confirmation of a supernova, they were a live broadcast of a stellar core collapsing into a neutron star, a process hidden behind light-blocking dust. For the first time, humanity didn't just see the universe, we heard it in the language of particles older than the solar system. Today, next-generation detectors like DUNE and Hyper-Kamiok and aim to tune into even subtler neutrino conversations, ones that might reveal why the universe is made of matter instead of antimatter, or how supernovae seed the cosmos with heavy elements. Each click is a breadcrumb on a trail leading back to the universe's most violent, most hidden events. So while neutrinos might be the quietest particles in existence, their whispers are rewriting the loudest chapters in astrophysics. And with every new detector, every refined experiment, we're leaning closer, straining to hear what else these cosmic ghosts have to say. Wormholes, those hypothetical tunnels through space-time, aren't just silent shortcuts between distant corners of the universe. If they exist, they might sing. Picture a cosmic hallway where every footstep echoes not just through space, but across time itself. While we've never detected a wormhole, the mathematics of general relativity suggests these space-time bridges could vibrate like plucked strings, resonating with the gravitational waves of passing stars, black holes, or even the faint tremors of the Big Bang's afterglow. Convert those vibrations into sound, and you'd hear something eerie, a deep, wavering drone layered with ghostly echoes that fade in and out as space-time itself stretches and recoils. These hypothetical sounds wouldn't just be cosmic ambience, they'd be a smoking gun. Unlike black holes, whose event horizons swallow light and sound, wormholes could theoretically allow vibrations to pass through their throats, creating interference patterns detectable from afar. Imagine two black holes merging on one side of a wormhole. The gravitational waves from that collision wouldn't just ripple outward, they'd funnel through the tunnel, emerging on the other side milliseconds, years, or even centuries later, depending on the wormhole's structure. The resulting sound would be a discordant echo, a cosmic déjà vu where the same event is heard twice, once directly and again as if whispered through a distant door. The pitch of these echoes could reveal the wormhole's shape and stability. A short, stable wormhole might produce clear, resonant tones like a note sustained in a cathedral. A chaotic, collapsing one could generate garbled screeches, spacetime's version of static, as its walls shudder under the strain of exotic matter. Some theories even suggest that traversable wormholes would hum at specific frequencies, harmonics dictated by the warping of space around them. It's like listening to the architectural blueprints of a tunnel built not from steel, but from the fabric of reality itself. But how would we ever hear such a thing? Today's gravitational wave detectors aren't sensitive enough to pick up these subtle reverberations, assuming wormholes exist at all. Future observatories, like the proposed LISA space antenna or pulsar timing arrays that use neutron stars as interstellar microphones, might catch these whispers if they're loud enough. Alternatively, if a wormhole's mouth happens to lurk near a star or gas cloud, its vibrations could perturb the surrounding matter, creating secondary electromagnetic signals, radio waves or X-rays, that we could translate into sound. It's a needle in a haystack search, but the payoff would rewrite physics. Here's the wildest part: wormhole acoustics might not just prove their existence. They could reveal whether these tunnels are usable. A wormhole's sound could betray hidden dangers, tidal forces that would shred matter, or instabilities that snap the tunnel shut mid-journey. A stable harmonic hum might suggest safe passage. A cacophony of screeches could warn of a one-way trip to oblivion, and if against all odds we ever detect a wormhole song, it won't just be a triumph of astronomy. It'll be an invitation to listen closer, to decode the music of shortcuts through space and time, and perhaps one day to step into the echo ourselves. Time itself might not be the silent, invisible river we perceive at the smallest scales. It could pulse with a rhythm, a faint acoustic signature woven into the fabric of reality. Theoretical physicists speculate that in the quantum foam, where space-time churns with fleeting particles and energy fluctuations, time's passage isn't smooth. Instead, it might tick in discrete steps like the second hand of a cosmic clock, each movement generating vibrations so tiny they're drowned out by the noise of the universe. These hypothetical sounds wouldn't resemble anything we know, no familiar hum or chime, but rather a series of quantum clicks, the universe's smallest metronome marking the intervals between moments. Imagine the universe as a grand piano, with each string representing a fundamental force or particle. Time, in this metaphor, wouldn't be the pianist's hand, but the resonance between the strings, the way vibrations from one note influence the next, creating harmony or dissonance. At the Planck scale, where time and space break down into indivisible units, these interactions could produce a form of sound, not through air or matter, but through the interplay of quantum fields. Some theories, like loop quantum gravity, suggest that space-time itself is granular, a mesh of interconnected loops that vibrate as they evolve. These vibrations wouldn't carry pitch or tone in the traditional sense, but their frequency could encode the rate at which time unfolds, a direct sonic signature of reality's clockwork. Why does this matter? Because if time has an acoustic footprint, it could redefine our understanding of the universe's most elusive phenomena. Black holes, for instance, might not just warp space, they could stretch time's vibrations into lower frequencies, creating a gravitational Doppler effect that distorts the sound of time near their event horizons. The Big Bang's aftermath might have left behind a faint reverberation, a quantum echo hiding in the cosmic microwave background. Even dark energies accelerating expansion could be traced through shifts in these vibrations, like a melody slowing to a crawl as the universe grows colder and emptier. The challenge is detection. Current technology is light years away from measuring such infinitesimal oscillations, but future experiments like ultra-sensitive atomic clocks synchronized across interstellar distances or quantum interferometers probing Planck-scale physics might one day pick up these whispers. It's like trying to hear the flutter of a butterfly's wings in a hurricane, but the payoff would be extraordinary. Proof that time isn't just a dimension we move through, but a dynamic, resonant force, as alive with texture as the cosmic symphony it conducts. Until then, the sound of time remains a tantalizing what if, a reminder that the universe's deepest secrets might not just be seen or touched but heard, in frequencies we're only beginning to imagine. And if we ever do tune into time's rhythm, it won't just be a breakthrough in physics. It'll be the moment we learn to listen to the universe's heartbeat. We're standing on the brink of a cosmic revolution, one where the universe's whispers will soon roar into clarity like never before. The next generation of telescopes and detectors isn't just expanding our vision, it's fine-tuning our ears to frequencies we've never been able to catch. Take LISA, the Laser Interferometer Space Antenna, slated to launch in the 2030s. Unlike its Earthbound cousin LIGO, which listens for the high-pitched chirps of stellar mass black holes, LISA will drift in space, free from terrestrial vibrations, its 3 spacecraft forming a triangle 2.5 million kilometers on each side. This colossal instrument will tune into gravitational waves far lower than anything we've detected, the deep, resonant hum of supermassive black holes spiraling toward collision in the hearts of galaxies. These aren't just fleeting signals, they're sustained tones, some so low they take years to complete a single oscillation. Imagine hearing the bass line of the cosmos for the first time, a soundtrack to the dance of giants that's been playing since the universe began. Then there's the Square Kilometer Array, or SCAR, a sprawling network of radio antennas across 2 continents, set to become the most sensitive radio telescope ever built. While LISA listens to spacetime's vibrations, SKA will capture the electromagnetic symphony of the universe, pulsars ticking like atomic clocks, the faint hiss of hydrogen clouds where stars are born, even the potential radio whispers of extraterrestrial civilizations. But here's what's groundbreaking. SKA won't just collect noise, it'll decode it with artificial intelligence. Machine learning algorithms will sift through petabytes of data, identifying patterns too subtle for human ears, anomalies that could reveal hidden pulsars, exotic physics, or signals from realms beyond our current understanding. AI isn't just a tool here, it's the ultimate cosmic translator, turning chaos into melody. But the most tantalizing possibility lies beyond even these projects. Some theories suggest that if the multiverse exists, if our universe is just one bubble in an infinite froth of others, collisions between neighboring bubbles could have left faint acoustic imprints in the cosmic microwave background. These wouldn't be ordinary sound waves, but space-time tremors echoing across dimensions, a hum from outside our reality. Future observatories, like the proposed CMB S4 experiment, could scan the sky for these anomalies, turning the afterglow of the Big Bang into a recording of something far stranger. It's like finding fingerprints on a windowpane, proof that something beyond was once pressing in. What's electrifying is how these technologies will work in concert. LISA gravitational waves could reveal black holes merging in the early universe, while SKA's radio eyes pinpoint their aftermath in swirling disks of gas. AI might then cross-reference these signals with data from neutrino detectors or gamma-ray telescopes, painting a multidimensional portrait of cosmic events. We're not just building better instruments, we're constructing an orchestra, each player tuned to a different part of the spectrum, all conducted by the laws of physics. And as this symphony unfolds, we might hear something even more profound, not just the universe's past but its future, the hum of dark energy's expansion, the murmur of protons decaying in distant epochs, even the final, fading notes of heat death itself. The universe has been singing for 13.8 billion years. Now, we're finally learning to hear every word. From the faint hum of the Big Bang to the roaring collisions of black holes, interstellar sounds are the universe's way of speaking to us, not in metaphors, but in literal vibrations that ripple through the fabric of reality. These cosmic whispers carry stories we're only just learning to decode. The deep, resonant pulses of colliding neutron stars tell us how gold and platinum are forged in stellar furnaces. The eerie crackle of interstellar dust reveals the raw materials of planets. Even the silence of dark matter hums with gravitational implications, hinting at the invisible scaffolding that holds galaxies together. Every frequency, every pause in the noise is a piece of a puzzle 13.8 billion years in the making. What's extraordinary is how much we've already learned by simply listening. Just a century ago, we thought space was silent, a vacuum where sound couldn't travel. Now we know the cosmos thrums with vibrations, from the high-pitched ticks of pulsars to the subsonic groans of supermassive black holes. These sounds aren't just curiosities, they're tools. The same way a doctor uses a stethoscope to hear a heartbeat, scientists use radio telescopes and gravitational wave detectors to diagnose the universe's hidden workings. When two black holes merge, their gravitational chirp doesn't just confirm Einstein's theories, it measures the warping of spacetime itself. The cosmic microwave background's faint static isn't just noise, it's a snapshot of the universe's infancy, a lullaby from the dawn of existence. And we're only scratching the surface. Imagine what else might be out there, sounds we haven't yet imagined, let alone detected. The quantum fizz of virtual particles flickering in and out of existence. The resonant hum of cosmic strings, if they exist, vibrating like galactic guitar strings, the distant chorus of exoplanet atmospheres where alien winds might howl through methane valleys or whisper across ammonia seas. With missions like LISA and the Square Kilometre Array coming online, we're on the verge of hearing frequencies previously drowned out by cosmic noise, tuning into channels we didn't even know existed. This isn't just about scientific discovery. There's something deeply human about the act of listening. Sound connects us emotionally in ways data alone can't. When you hear the haunting drone of a black hole's accretion disk or the rhythmic ticking of a pulsar, you're not just processing information, you're feeling the universe's scale, its violence, its beauty. It's why projects like NAS are sonification programs which turn telescope data into audible melodies resonate so powerfully. They remind us that the cosmos isn't a static museum exhibit. It's a dynamic, evolving performance, and we're both audience and participants. So the next time you step outside on a clear night, look up and imagine the symphony overhead. The stars aren't just points of light, they're instruments in a grand celestial orchestra, each playing its part in a composition older than time, some notes we've learned to recognize. Others remain mysteries, waiting for the right moment and the right technology to reveal themselves. The universe has been singing since the beginning. And as long as we keep listening, it'll never run out of stories